Section 1.5, Volume and Surface Area. So this is the three-dimensional section where we're going to look at three-dimensional space and some of the measurements that we might take in this space. So to start out, let's talk about volume. And this measures how much space in three-dimensional space an object takes up. Okay, so volume is a three-dimensional measurement, so the units of volume are always cubed. In the previous section, we were looking at some two-dimensional objects, and we were looking at measurements like area. And remember, like if we were given units in terms of feet, the area that we would find in some of those problems, the units would be feet squared. So if we are looking at a three-dimensional object, where the measurements were taken in terms of feet, then the volume would be given in cubic feet, or feet cubed, like this. Okay, and then the other important measurement we're going to focus on is surface area. And this measures the total amount of area on the surface of a three-dimensional figure. You might think that the units of surface area would be, cubed, like feet cubed or something like that. But it actually isn't. It's measured in terms of units squared. And this is because if we're looking at a surface, that is a two-dimensional object. So three-dimensional objects might be built up out of planes, out of, like looking at these rectangular solids down here, like looking at the 6 sides of this type of shape. Really, we're taking 6 two-dimensional objects and putting them together to form a three-dimensional object. So surface area is an area, and it'll be measured in units squared. So we'll have to be careful of that. Let's get into some formulas. We'll start with rectangular solids. These are kind of the most basic three-dimensional shapes that we'll see. And rectangular solids are just where we have right angles all around, so let me mark these out, right angles here and all over the place, right? So taking a bunch of rectangles and putting them together. The volume of a rectangular box can be found using the formula V is equal to length times width times height. So length, and it doesn't really matter what you call length, width, and height, but we could call, how about this dimension length, this dimension width, and this dimension height. Okay, so pretty much the 3 measurements that determine the shape of this solid. Multiply them together, that gives you the volume. The surface area of a rectangular box can be found using the formula S is equal to 2 times length times width plus length times height plus width times height. All right, and where this comes from is think about each of these surfaces, right? Remember I was saying that we sometimes put a bunch of two-dimensional surfaces together and they form a three-dimensional object. If we wanted to find the surface area, we're just trying to find the surface, the area of each surface that makes up this shape. So looking at this front surface right here, what would be the formula for that? Well, it would just be base times height, or in this case, width times height, right? And over here, this would be length times height, and this surface up on the top would be width times length, or length times width, doesn't really matter. And then of course we have the side on the back, we have the side on this side, and the side on the bottom. And that's just going to be, repeating those 3 areas that we just computed, right? So if you add all those together, we end up with this formula. So just looking at where that formula came from. Now let's see how we might apply these formulas. We have this shape here. We're given this picture. It's a volume. This is in three-dimensional space. And we want to find the volume and the surface area of this shape. So this looks like kind of a compound shape or a composite shape. Like I'm seeing various rectangular boxes here, and I'm trying to break this down visually, kind of mentally, in terms of a finite number of rectangular boxes because I have nice formulas to work with rectangular boxes. So what are ways that I could sort of subdivide up this shape, just so I have a few boxes? There are a few ways to do it. I could think of, this rectangular box right here, and then this rectangular box right here. That's one way that I could split it up. I could also break it into these two boxes. There's this tall vertical box right there, and then this box over here. Okay, so I think I'll use this. It isn't going to be any easier or more difficult to do it one way versus the other. Just pick one and run with it. So I'm going to split it into these two shapes, and I'm going to find the volume. Yeah, this what I'm doing here is kind of focusing on finding volume. So let's start with this. Let's find the volume. And I'm just going to find the volume of these two separate boxes and add them together, and that will give me the volume of the entire shape. All right, and looking at the dimensions that are given in the picture, this length right here is 10 centimeters. That's going to apply to both of these rectangular boxes. So maybe I'll color code my work, and let's start with finding the volume of the red box. So like always, it's going to be length times width times height. And what is the length, width, and height of that red box? Well, I see this dimension right here is 3 centimeters. This dimension down here is 7 centimeters, and this dimension is 10 centimeters. So what I'll do here, I'll write it down here. This is going to be 7 centimeters times 3 centimeters times 10 centimeters. Okay, and it doesn't matter the order in which you list these factors. Remember, multiplication is commutative, so you can change the order. It's not going to affect it. Okay, multiplying these together, I get 210. And what are the units going to be here? I deliberately listed these units here. Centimeters, centimeters, centimeters. Multiplying all three of those together, I'm going to get centimeters cubed. All right, so there are those cubic units that we are expecting since we are finding a volume here. Okay, so that is the volume of that red box. Let's do the blue box now. Again, length times width times height. For the blue box, what do we have? We have, okay, we have to be careful here because this 8 centimeters, the 8 centimeters really gives us this whole distance right here, right? So if I'm trying to find the width of just the blue box, so just this width from here to here, I'm going to have to do a little subtraction. Right, so how could I find this? Maybe I'll call this the width, W. Well, this little measurement right here, the width of this previous box, the red box we were just talking about, is 3, right? So then 3 plus W should give us 8 centimeters. Maybe I'll just do this side work right here. 3 plus W should be equal to 8, so subtracting 3 from both sides, it looks like W is 5 centimeters. Okay, but now that I have that, the height is 4 centimeters, the length is 10 centimeters. So I'll do 10 centimeters times, and then 5 centimeters, that value we found, times 4 centimeters. All right, looks pretty good. I'll multiply these three numerical values together and I get 200. And the units are centimeters cubed. So the total volume is going to be the sum of these two values that I just found. So it'll be 210 centimeters cubed plus 200 centimeters cubed. And from that, I'm getting 410 centimeters cubed. I'll box that up. That's our volume. Okay, great. Let's talk about surface area now. Okay, I'm going to, I could use these same two boxes to sort of break up and find the surface area, because I'm seeing a lot of rectangular surfaces, for sure. The weird surface that I see in this picture is this kind of L-shaped surface right here. And I don't have a formula for L-shaped surfaces, so I'm gonna sort of continue with this interpretation of having the red box and the blue box, and we'll kind of work off of that. The surface area, for a shape like this, I'm not necessarily gonna be thinking about this formula, because this isn't just a rectangular box. Like, I'm just gonna be looking at a bunch of two-dimensional rectangles, and I'm gonna add them all up. So it's gonna be the sum of a whole bunch of surface areas. Let's see if we can figure this out. So I'm going to find a couple of measurements, because there are certain rectangles that are standing out to me. One that stands out to me is this one. Right, because I know that the length of this is going to be 10, right? We have that long measurement of 10 centimeters. But what is the height of that? I'll have to do another little subtraction problem, right? Because I'm running out of colors here. But if I want to find that height right there, maybe I'll just call that H. The total height over here of this whole entire shape is 7 centimeters. And I want to subtract from it this height right here, which is 4 centimeters. Okay, so 7 minus 4, that tells me this is going to be 3 centimeters. Okay, so here, just cleaning up my picture a little bit. That's 3 centimeters. We found that this was 5 centimeters right here. So I think I have everything I need now. So now I just want to stay organized and start adding up all of these surface areas. There are many different ways that we could approach this. Some people might do some kind of numbering system, like, okay, here is area 1, here's 2, here's 3, here's 4, and so on, and kind of work their way around. And you could do that and it'll work, but it's kind of tedious. What I'm noticing about this shape is we have a bunch of rectangular boxes. So if we're looking at the side, for example, like this whole side, this kind of L-shaped area right here, notice that the one on the other side back here is going to be exactly the same surface area. So I might divide up this surface area. So total surface area is going to be equal to, there's the side, right? The L-shaped side. So I might say like 2 times the sides, or 2 times side, because there's 2 sides, right? And then I'll add that to, okay, so that takes care of both of those sides. There's the tops also, right? So there's like the tops. So that would be like this area up here and this area down here. And then add that to the surface area of the bottom. And then we could add that to the, I'll call them the fronts, which are highlighted there. And the last thing would be add that to the back. Okay, so I might divide it up like that. This is one strategy. I can sort of simplify this a little bit though. And this takes just a little bit of geometric reasoning. Since these are all rectangles here, the tops and the bottom are actually going to be the same. So the tops, this region up here, plus this region up here, if we add those together, notice that it's just going to make that rectangle, which is the same surface area as the rectangle on the bottom. So I can kind of simplify this as, okay, I'll keep it as 2 times the side plus, and it's just going to be 2 times the bottom. And I'm using the bottom because that is just a simpler shape. It's just a single rectangle, so less work. And the same is true for the fronts and the back. If I add the fronts together, notice that the highlighted region there is going to be the same area, surface area, as that on the back. So this is actually going to be the same as just 2 times the back. Okay, and again, I'm choosing the back because it's only 1 rectangle rather than 2 rectangles. Okay, so there are many different ways that you could do this, but I'm just trying to reduce the amount of multiplication that I do in this problem. Okay, and now that I have this, okay, let's start actually plugging in some numbers here. So 2 times the area of the side. So let's focus on this L shape. It's actually the sum of 2 areas. It'll be 7 times 3 plus 4 times 5. Okay, so that's like the red box, you know, the area of the red box, and then the area of the blue rectangle, I should say. Okay, and then I'm going to add that to 2 times the bottom. So what is the area of the bottom? Well, that's just that whole platform, you know, the whole footprint of this shape, which is 8 centimeters times 10 centimeters. And I'll add that to 2 times the back, which is 7 times 10. All right, and I'll simplify this a bit. This will be 2 times 21 plus 20, so I'm getting 41 right here, plus 2 times 80, plus 2 times 70. And I'm not writing in the centimeters just because it would be too much work. I know that my answer at the end is going to be, I'll let you think about it before I tell you. All right, simplifying a bit more, this is 82 plus 160 plus 140. So it looks like I am getting 382, assuming all my arithmetic is correct here. I think we're good. Okay, and then what are our units going to be for this surface area? Yes, I know we're talking about a 3-dimensional object here, but area is a measure in 2-dimensional space, right? We're just adding up the area of a bunch of 2-dimensional rectangles here. So this is actually going to be in centimeters squared. And this is our surface area. Okay, so we will definitely be using these formulas, but a lot of the challenge of many of these volume and surface area problems is just like, how can we carefully divide up these shapes and kind of divide and conquer and use these very simple formulas we have and just apply them to, you know, multiple sides of a shape, or splitting up a shape into multiple volumes so that we can use simpler formulas and add them together. All right, so that's our first example. We've got another one here. Example 2, Mark wants to make an open box from an 8.5 inch by 11 inch piece of paper by cutting squares out of each corner, folding up the sides, and securing with tape. How much volume how does the volume of the box relate to the size of the squares he cut out? So for some of you, especially those who took college algebra with me, you might recognize this type of problem. Here's what's happening. We're making an open box out of a single piece of paper. So imagine an 8.5 by 11 piece of paper, right? It looks like this. I'll do it sideways. What this is saying is we're going to cut out squares from each of the corners. Okay, so imagine cutting out those squares. So here, maybe I'll give you like a stage 2. So the next stage is we now have this shape. And I apologize in advance for my drawing. It's much easier on actual paper. Okay, so we get a shape like this, right? And we cut out those squares. And what we want to do is fold along these lines so that those resulting flaps will come up and create the sides of a three-dimensional box. So the last step is you fold up those flaps and you end up with a shape that looks like this. Again, sorry, my drawings are not great, but I hope you get the idea. Okay, so cut out those corners, fold up the flaps, you get a box. Now, the question, what we're trying to determine is how does the volume of the box relate to the size of the squares that we cut out? Because notice there are a lot of different ways that we could cut these squares. Like we could cut really tiny squares. Like if we cut really small squares out of this box or out of this piece of paper, we would end up with a box that's like very shallow. You know, it's like a very shallow box, but it might be really wide, right? Or if we cut the squares to be really large, we would end up with a box that was like really tall, but it wouldn't be so wide. It would look more like this. Right? So depending on how big these red squares are that we cut out, it's going to affect the volume of the box that results. So the question is how can we relate the volume to the size of these squares? Well, we're going to have to set up a variable here because really we're trying to set up an equation that has this variable, you know, let's call it x, how about, as the independent variable in some volume formula for this box. Okay, so I'm just going to define, and you know, we could use x inches since, you know, we were given these values in terms of inches. So since these are squares, both sides are going to have the same measurement. They're both going to be x. Okay, so now when we fold up these sides, the height of the box is going to be x, right? Because the height is really determined by how large these cutouts are. Now, how about the other dimensions? Because to find the volume, we're also going to need to know what is the width and what is the length of that box. So how can we find those? It's tempting to say that the width and length are going to be 8.5 and 11, since those values were given to us. But remember, 8.5, that's this measurement here across the entire piece of paper. So that's 8.5 inches. And this width right here, you know, that long dimension, that's the 11-inch side of the original piece of paper. So when we fold up those flaps, that's going to be the actual base of the box. And there's going to be, you know, X inches subtracted from each side. All right, so the width is not going to be 11. It's going to be 11 minus x on this side minus x on this side. So 11 minus 2x. So here's what our formula should look like. Volume, of course, it's always length times width times height. But in terms of x, v of x is going to be equal to, okay, so the length is 8.5 minus 2x, again, because we lifted up those two flaps and that gets taken off of the length, times width, which will be 11 minus 2x, because of, and I'll highlight them, so it's 11 minus 2x because of this flap getting folded up and this flap getting folded up. And the last dimension is the height, which is just x. Okay, and we're done because we just wanted to find some formula to relate the volume of the box to the size of the squares that were cut out. And there it is. So, you know, maybe I could just note that the volume here, the units of this is a three-dimensional shape, volume is a three-dimensional measurement. This is going to come in the form of units cubed, and since we're working with inches, you know, the 8.5 and 11 were inches, so this is going to be inches cubed. All right, that's it for example 2. Let's talk about irregular solids. If an object has a congruent top and base and all sides are perpendicular to the base, then the volume of the object is given by this really nice formula, which is just the area of the base times the height. Okay, so what this is saying here is if the two sides, you know, like this side in this image, this top and then the base, if they're congruent, if they're the same shape, and it's just like this two-dimensional shape has been stretched through space, and these are all right angles here, then the formula for the volume is just going to be whatever the area of the base is times the height, how far it was stretched. So looking at example 3, we have this kind of triangular shape that has been stretched through space, and we're given the dimensions. This is a 9 by 9 by 9 triangle. So this is a special type of triangle. I don't know if you remember what we call it when all three sides are congruent. This is called an equilateral triangle. Remember, isosceles is when two sides are congruent, like a 45, 45, 90 triangle is isosceles. This is actually equilateral. Okay, and this triangular shape is just being stretched 4 inches. Okay, so we're creating this 4-inch tall little triangular thing. So to find the volume of this, the volume is just going to be the area of the base, which is that triangle, times the height, which is 4 inches. So the hard part of this problem is just finding the area of that triangle. So how do we want to do it? It's a 9 by 9 by 9 triangle. How do we want to do this? Since it's not a right triangle, I can't just jump into 1/2 base times height. So there are multiple ways that I could approach this. I could use Heron's formula, where you calculate, you know, what is that S value, and then use the formula square root of S times S minus A times S minus B, blah, 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 which is kind of a laborious process. There's another way that we could do this, and I think I might try it this way. An equilateral triangle has 3 congruent angles. The measures of all of these angles are going to be the same. And they're all 60 degrees, right? They have to be 60 degrees if they're all the same because they must add up to 180, right? So pretty much take 180 degrees, divide it by 3, and you get 60. That tells us what all those angles are. And I'm talking about this because if I wanted to determine the height, like if I wanted to just use the sort of simpler formula for the area of the triangle, 1/2 base times height, right? And this is special height. This is like the height of the triangle. And then eventually we'll multiply by the height of the whole shape. I would drop a perpendicular down here, right? So I'm just dropping a perpendicular line, and that would be the height. Whatever the length of that is the height. So how could I find the height of that? And maybe I'll draw a little side picture here just so we can see what's happening. You know, we have this equilateral triangle, doing my best to make it look equilateral. Drop a perpendicular, right? We know that this side length is 9. How can we find that height? There are a couple different ways we could go, but it all relies on the fact that this is an equilateral triangle. So this is a 60-degree angle. This is a right angle. What angle must that be up there? It must be a 30-degree angle. Okay, so what we end up with is a 30, 60, 90 triangle. So let me draw that out a little more precisely. God, I'm so bad at drawing triangles with this weird stylus pen thing. So I just drew this triangle right here. Okay, that's 60 degrees, that's 90 degrees, that's 30 degrees up there. And I know that this side length is 9, and I want to find this side length. Well, remember with 30, 60, 90 triangles, the short leg is going to be half of the length of the long leg, so this is going to be 4.5. Okay, you could also think that this is just halfway across that length of the big triangle, the big equilateral triangle we started with. So what is this going to be based on our proportions that we know for 30, 60, 90 triangles? Remember, it's like this. It's like this is x, this is 2x, and this is x root 3. So the side length on this side is just going to be 4.5 times root 3. Okay, so now that I've determined that, I can say this, the formula, just substituting in the values I have, it'll be 1/2 the base, which is 4.5, and this is measured in inches, I guess I could put that in there, times the height of the triangle, which is not a super nice number, but we have it, 4.5 root 3, again in inches. And I'll multiply that by the height of our three-dimensional shape, which is 4 inches. All right, so working carefully, trying to stay super organized. Now I am going to reach for my calculator and see what we get out of this. So multiplying together, we'll do 4.5 times 4.5 times root 3. Okay, and then times 1/2 times 4. And I'm getting this. I'm getting a volume of 70, and you know what, I'll round this. I'll round it to 2 decimal places, 1.5 inches cubed, because we're talking about a volume in this case. Okay, so that's the approximation. You could have gotten an exact answer here. I would have written it a little bit differently. You know, to get an exact answer, I would have written like 1/2 times 9/2 for 4.5. Okay, and I think I would have gotten 81√3/2. Yep. So that's another way, if you wanted to get an exact answer, or if the problem was requiring that you do that, I would have expressed it this way. But on a quiz or a test, I am totally flexible. Really, I would be happy with either of these answers, as long as you show these clear steps leading up to that answer. Okay, so overall, all that we did here is just we found the area of the base, which was triangular, multiplied it by the height, and we got the entire volume. Okay, we just had to use some tricks to find the area of that base. All right, example 4, we have a drum here, and we want to compute the volume of this drum. Your answer should be written in terms of R and H. Notice we're not given numerical values for R and H. We are just asked to express this volume in terms of R and H. This is sort of like the problem that we did up here, where our answer came looking sort of like this formula here, rather than just a numerical value. So let's do the same thing here. Now, this is a drum. This is like a cylindrical drum here. So we can see that this circular shape has been stretched and kind of projected through three-dimensional space. And we're given this height of h. So to find the volume, it will be the area of the base times the height. Now, how do we find the area of that base? Well, it's a circular base. All we need to find the area of a circle is the radius, which is given as just r. So the area of the base will be pi r squared. That's our formula. And we multiply that by the height. So we can drop the parentheses here and just write this as, the volume is equal to pi r squared h. And I'll put a box around that. And what we just did is we just derived the formula for the volume of a cylinder. So here it is down here. Here's our cylinder. The volume of the cylinder can be found using the formula V equals pi r squared h, which we just found. How about the surface area? We're given this formula, S is equal to 2 pi r h plus 2 pi r squared. So where did this come from? Remember, the surface area is just adding up the area of all of the surfaces around the entire three-dimensional shape. So what do we have here? We have the surface on the top, right, which is circular. So what's the area of that surface on top? Pi r squared. How many of those do we have? We have the top and the bottom. So we have 2 pi r squared. That's where that second term in the formula came from. And then we also need for the surface area, the area of this piece wrapping around here. How could we get the area of that surface there? Well, imagine taking that surface, like if this was a can or something, imagine cutting around, right? Cut off the top, cut off the bottom, and unroll the side. And we're going to get this rectangular shape right here. What are the dimensions of this rectangular shape? Well, the height is just going to be h, right? That's already given to us. What is this length going to be? Well, that length is just the distance around this circle. What do we call the distance around the circle? The circumference. What's the formula for the circumference of a circle? 2 pi r. So the area of that right there is just going to be base times height. It's going to be 2 pi r times h. 2 pi r times h. Okay, so see how we just kind of quickly, informally derived this formula for the surface area of a cylinder. Okay, if you are kind of intrigued by this process of working in abstraction and just kind of deriving these different formulas, this is what mathematicians do. Of course, it gets a lot more complicated than what we were just looking at. But if this way of thinking at all tickles your fancy, you might want to consider a major in math, because we do this all day long. At a certain point, you won't even be writing numbers on the page. It'll just be a whole bunch of letters and reasoning. But anyway, there are two formulas for cylinders. Right circular cones, for those of you who didn't like the derivations, don't worry, I'm not going to make you do it for this. But you could certainly play around with that if you are interested. A right circular cone is just a cone that looks like this, right? We've got circular cross section, so if I were to cut straight across at any point, we would have a circular cross section. And it's right because the direction in which this extends out is going to be orthogonal or perpendicular to the circular base. So we'll have a right angle right here. So that's what makes it a right circular cone. The volume is given by this 1/3 pi r squared h, so really not so different from this formula, just multiplying the volume of a cylinder by 1/3. And the surface area is given by this formula, pi r times r plus square root of h squared plus r squared. Okay. That square root of h squared plus r squared might look kind of familiar. It comes from the Pythagorean theorem. It has to do with this side length right here. It turns out that side length is the square root of h squared plus r squared. But I'm going to stop myself before I derive the whole formula for you. Okay, let's try an example here. A paper water cup is in the shape of a right circular cone with a height of 2.5 inches. So I don't know if you've seen those little paper cups that they give you that are shaped like this. I think so you can't set it down. They don't want you to set down your drink or something. I never fully understood why they did that. But anyway, we're dealing with one of those water cups. And it has a height of 2.5 inches. If the volume of the cup is approximated at 2.6179 inches cubed, then what was the approximate radius of the cup? So this is sort of interesting because we're given the volume and we're asked for the radius, right? And we're given the height as well. So let's see if we could figure this out. I know that the volume, actually let me draw a picture first just to make sure that we are in agreement about what this shape looks like. It looks something like this. I don't know exactly what the proportions are going to look like in the end, but I know that this height, right, which is really the distance from the center of that circle to the vertex, that point up there, that height is 2.5 inches. And the volume is this number here. So the volume of this shape, I know the formula is 1/3 pi r squared h. Let me substitute in these values I have. I have 2.6179. 1/3 in pi can hang out there. R I don't know, so I'll leave that as a variable. H, I'm going to substitute in that 2.5 inches. And I'm not listing the units for now, just for the sake of simplicity. All right, so now I'm trying to solve this equation for R. So let's do that. I'll start by, how do I want to start? Well, I want to get R by itself, so I can divide both sides by 2.5. I can also divide both sides by pi. And I'm trying to get rid of that 1/3. I can achieve that by just multiplying both sides by 3. Okay, so sort of doing a lot at once now, but this should work. So I'll multiply 2.6179 times 3. I'll divide by pi, and this of course is done on the calculator. I'll divide by 2.5, and I am getting this number, 0.9999964 blah blah blah. I don't really care beyond that. I'm going to approximate this. I'm going to round to the nearest thousandth even, and it just gets me to 1. Okay, so I'll say 1 is approximately r squared. Okay, and I put the approximation, the little squiggly equal sign at this step because this is the step at which I rounded. And okay, how do I finish this? I'll solve by taking square roots, right? So take the square root of both sides. And remember, when we take the square root, it introduces a plus or minus technically. The square root of 1 is just 1. However, since we're taking a measurement here of a radius of some physical object, we don't have negative measurements in 3-dimensional space. So we're just going to take the positive value. So r is approximately equal to positive 1. And what are the units? It would be inches. I'll box that up. Okay, so using the correct formula, substituting in values in the right places, and solving for the variable r. Okay, so the radius of this cup is 1 inch. Example 6, this is kind of a trippy one. We want to find the volume of the space between the cylinder and the cone shown below. So we're trying to find the volume of this shaded shape here. And I don't know what to compare this to. It sort of looks like a skateboard wheel or something. So this cylinder in here is actually empty space. Okay, and the height of this object is 12 inches. Okay, and maybe I should specify that. I guess it's maybe sort of ambiguous. The height of the entire shape is 12 inches. Okay, so this cone really comes and just touches the edge of the cylinder. So how do we find the volume of this shape? I think we're going to have to use some kind of spatial geometric reasoning here. And because this is an odd shape, like we don't have a formula for specifically a cone cut out of a cylinder. Like you didn't see a formula for that up on any of these previous pages. So I think that we're going to have to use subtraction, right? We're going to have to find the difference between the volume of the cylinder and the volume of the right cone. So let's do that. So the volume of the cylinder, and I'll just do this, like use a little subscript to show which volume I'm finding. So the volume of that is just going to be pi r squared h. Okay, and I have the radius and I have the height. So this is going to be pi times the radius squared. The radius is 12 inches. And you know what? I'm going to put in the inches. I'm going to put in the units just so we could see how we end up with inches cubed. Okay, so that'll be squared. We'll multiply that by the height, which is 12 inches. And simplifying this, I get pi times 144 inches squared, right? Applying that second power to both of those, times 12 inches, like that. And then I'll do 12 times 144, and I get 1,728. I used my calculator for this. Times pi, And multiplying inches squared times inches, that gives us inches cubed. Okay, so I just wanted to demonstrate that we get inches cubed, which is what we would expect for a volume. Okay, now let's find the volume of the cone. Pretty similar formula here, just 1/3 pi r squared h. Okay, so 1/3 pi, and we have the same values, right? 12 inches squared times 12 inches. All right, so multiplying all of this out, we end up with 576 pi inches cubed. All right, I'm leaving this in terms of pi because, as soon as I multiply by 3.1415, blah, 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 I'm going to get an approximation. I'd rather stick with an exact answer for now. So now the volume of the entire shape, so I'll just call this, V. This is going to be the difference, the volume of the cylinder minus the volume of the cone, which will be 1728 pi inches cubed minus 576 pi inches cubed. All right, and to take this difference, I can treat these two terms like terms. Notice that they both have pi inches cubed. Right, so we can treat it like terms where the variable part, which isn't variable in this case, but I could sort of think of it that way, is pi inches cubed. Like if we're going to take the difference 1728x minus 576x, we would just subtract the numerical values. We'll do the same thing here. And I'm getting 1152 pi inches cubed as the volume for the entire shape. So I can put a box around that as my answer. I can also multiply, like if I wanted to get a decimal approximation, sometimes it's helpful to have that. I'll include that as well. And I just multiplied 1152 times pi, and I got 3,619.114737. It keeps going. I'll just round to the nearest tenth. How about? I'll do 0.1 inches cubed. Okay, and like I said for an earlier example, on a quiz or a test where you're giving me handwritten work, I'm generally happy with either of these answers. If I don't specify, sometimes in the problem I'll say round to the nearest tenth or round to the nearest hundredth, or provide your answer in terms of pi. If I don't give specific instructions, I'm flexible on how you give your answer, and I think your homework program on Canvas is usually the same way. But there we go, just taking the difference of those volumes to get our answer. Let's look at spheres. Spheres are really nice because we don't have a radius and a height, we just have a radius. So it's kind of like finding the area of a circle. You only need that one measurement. For spheres, to find the volume, the formula is just 4/3 pi r cubed. Very nice. And the surface area is just 4 pi r squared. All right, example 7. This is the last problem in this section. A bead is created from a sphere by drilling a cylindrical hole through the sphere. The original sphere has a radius of 13 millimeters, and the cylinder drilled through the center has a radius of 5 millimeters. So just sizing this thing up to begin with, that is 13 millimeters, and the radius of the cylinder, that's just that distance there, is 5 millimeters. So we've got a few parts here. Part A, we want to find the volume of the sphere, but before the hole was drilled. So really we're just looking at the spherical object that we started with. And the volume formula for a sphere is 4/3 pi r cubed. And yeah, a really nice one. We only need that radius value in order to find this volume. So the radius is 13. And I'll write the millimeters in here. Okay, you don't really need to write millimeters in there if you know what the units are going to be at the end of the problem, but sometimes I like to do it just to demonstrate why we end up with millimeters cubed in this case. So anyway, I'll multiply all this out, definitely use my calculator. I don't know what 13 to the third is. Okay, and then, yeah, 13 to the third, multiply that by 4, divide that by 3. I don't get a super nice number. I might write it like this first. So 13 cubed is 2,197. Multiply that by 4 and we get 8,788. Haven't yet divided by 3, and I haven't multiplied by pi. But I'll have this in terms of millimeters cubed. Okay, so that's actually about as good as we can do for an exact answer as far as having it simplified, because that 8,788 is not nicely divisible by 3. But if I want to get a decimal approximation, I could divide by 3 multiplied by pi. Again, I can do this using my calculator. And I get, and I'll round this to maybe just a couple of decimal places, I get 9,202.77 millimeters cubed, or cubic millimeters. Okay, so either of those last two are fine. That's just our approximation there. Okay, so that's just the volume of that sphere. Now let's start thinking about this cut that we make where we drill a hole through the center of it so that we have this bead shape. Part B in this question, we're asked to find the height of the bead. Okay, and this should be equal to the height of the cylinder that gets cut out of this shape. So notice, looking closely at this picture, we have some dotted lines. This is going to be removed when we drill the hole. Right? So the height of this bead, you might think that it's going to be just double the radius. It's just going to be the diameter of the original sphere. You might think that it's going to be 26, but it's not going to be because we cut that piece off there. So how are we going to find just the height of the cylinder, right? Just that length right there. It's definitely not given to us. Let's think about the two numbers we have. We have 13 millimeter radius for the sphere. We have 5 millimeter radius for the cylinder. I'm going to sort of erase these for a second. If I'm trying to find that red length there, that's the same as just 2 times this distance right here. Okay, that's like half of the height of the cylinder. And the reason why I'm drawing that in, and that's going to be helpful to finding the height of the overall cylinder, is I can create a right triangle where I know the length of 2 of the sides. I can use the radius of the cylinder, which I know is 5. I can use the radius of the sphere, which I know is 13, just looking at the specific radius going from the center to this point at which the cylinder intersects with the sphere. And this is going to be a right angle right here. So we have a right triangle. Okay, so hopefully you kind of see where I'm going with this. I think I should be able to find this. I might just label it, I could label it X, I guess. let's use what we know about right triangles to solve for x. So what formula or theorem is going to be helpful for finding x? Well, whenever I have two sides and I'm looking for a third side of a right triangle, the Pythagorean theorem allows me to do that. Okay, so the Pythagorean theorem, this tells me that x squared plus 5 squared is equal to 13 squared. Remember, the hypotenuse is the one, that's the value that goes by itself. And I can simplify. This is x squared plus 25 equals 169. And I'll subtract 25 from both sides. And I get that x squared is equal to 144, which is a nice number. That's a perfect square. I like that, because I'm going to take the square root of both sides, and I'll get that x is equal to plus or minus 12. But I am just going to take the positive value because we're talking about, a measurement, a physical measurement, half the height of this cylinder. So I won't worry about the negative value. Take that away. And my units are millimeters. Okay, so x is 12, so then what is the height of the bead? Well, the height is just going to be 2x. Okay, so taking this, then our height h is going to be equal to 2x, which is 2 times 12 millimeters, which equals 24 millimeters. I'll put a box around that. Nice. Now that I have the height and the radius of the cylinder, I should be able to answer part C, because part C is asking what is the area of the inside surface of the bead. The inside surface of the bead is just going to be the surface area of this cylinder here. Okay, and we have a formula for this. I'm not even gonna really memorize the formula though, because I always just think, remember that picture we saw where you unroll, you take a cut on one side of this cylinder and unroll it, and you end up with a rectangular piece where that dimension is the height, and then the unrolled sort of long piece is just going to be the circumference of the circle that defines this shape. So it's just going to be 2 pi r. And we have r, the radius is 5. So really to find the surface area, I'm just looking for, so I'll say surface area is equal to the product of these two values, so 2 pi r and then times h, which should be what I wrote on the page a couple pages back. We can check. Yeah, so the surface area, this surface area formula here actually includes the top and bottom. That's where the 2 pi r squared comes from. So really we're just looking for the area of this outside bit. Okay, because we're trying to find the surface area of the inside of the bead, so we're not including the top and bottom, right? This is just a hole, this is empty space. So there you go. If you didn't sort of take the geometric reasoning approach to this, you might have copied down the incorrect formula. So there we go, surface area. We just want to compute this. Let's substitute in our values. It'll be 2 pi times r, which is 5 millimeters, times h, which is 24 millimeters. Multiplying together, I believe we'll get 240 pi millimeters. And that's one way you could write your answer. That's the exact answer, which I would actually prefer in most scenarios. But just in case you're asked for a decimal approximation, you could multiply using your calculator, and I'm getting rounding to 2 decimal places. How about 753.98? Oh, sorry, this should be millimeters squared, right? Because I multiplied millimeters times millimeters, not millimeters squared. So either of these would be just great as answers to this. Okay, I love this problem. If you see bead, spherical bead type problems, don't be surprised if you're using the Pythagorean theorem at some point. Drawing a little triangle there using the radiuses, or the radii, I think is the plural. So yeah, great problem to study from. You might see something like this on homework or quizzes or maybe even a test, who knows. That's the end of section 1.5. Up next, we're moving into the rectangular system, Cartesian coordinates, x coordinates, y coordinates, more familiar stuff. So I'll see you in that next video, 1.6.